So a rocket is floating in the middle of the Indian Ocean right now, 812 nautical miles from the nearest port. And the man who runs the company that built it just posted online that they're sending a ship to go get it. Simple, right? Send a ship, hook a line, pull it home. Except the moment someone with actual towing experience pointed out that this might not be simple at all, the internet turned on him. Let's orient ourselves here before we get into this, because there's a real technical argument buried under all that noise. And by the end of this video, you'll understand exactly why towing something across open ocean is nothing like towing something in a harbor, and why the confidence in that original post might be running ahead of the physics. If you're new here, take a second, subscribe to the channel, and hit the bell so you don't miss what happens when this tow actually gets underway. Because this story is moving fast, and there's a real chance it ends in failure, not success. Where are you watching this from? Is this the kind of maritime story that reaches your part of the world? Or is this the first time you've thought about what it actually takes to recover something the size of a building out of open water? Now let's lay out what actually happened, because the sequence matters. On July 24th at 5:51 in the evening Eastern Time, a Starship vehicle lifted off from Starbase, Texas, on its 13th integrated test flight. This was the second flight of the third-generation Starship and Super Heavy vehicles. 33 Raptor engines ignited on the booster and pushed the stack up over the Gulf. After a hot staging maneuver, the upper stage, the Starship itself, lit its own engines and continued on to space, where it deployed a set of next-generation Starlink satellites. That part of the mission went the way it was supposed to. Then came re-entry. The upper stage came back down through the atmosphere, gathered data on its heat shield, and guided itself using its flaps toward a pre-planned splashdown zone in the Indian Ocean. It relit its engines, executed a landing flip and a landing burn, and came to rest intact on the surface of the ocean. Understand something important here. This was not supposed to happen. The upper stage on these test flights is not designed to be recovered. It is designed to survive re-entry, prove out the heat shield, and then break apart or sink. Nobody built recovery hardware into this vehicle because nobody planned to recover it. And yet, there it was on July 24th, floating, intact, riding high in the water. There was a vessel called the Go Australius already in the area. It was there to observe the splashdown and pick up any debris that survived on the surface, because that's what everyone expected. Debris, not a whole vehicle. Instead, they got a whole vehicle. For several days after the 24th, the situation was mostly quiet. Then, on July 28th, the founder of the company posted publicly that they were sending a ship out to recover Starship. That single sentence is where this whole story turns into a maritime problem instead of a space problem. Because recovering something and towing something are two very different operations, and the moment you commit to a tow, you inherit a whole set of physical constraints that don't care how good your rocket engineers are. Here's the pushback that got posted in response to that announcement, and it's worth repeating carefully, because it's the actual technical core of this entire episode. Unless the vehicle is configured for open ocean towing, with hard points built in, specifically to attach a bridle, an open ocean tow is going to be difficult, not impossible. Difficult. That distinction matters, and we're going to spend the rest of this video proving why. Understand, towing normally involves attaching to points on a hull that are built to withstand the combined weight of the object, the water resistance against it, and the dynamic hydrodynamic forces of being dragged through open ocean swell. Those points don't exist by accident. They're engineered in during construction because someone planned for this vessel or object to be towed someday. Nothing about this Starship's design suggests that kind of planning. It was built to fly, re-enter, and either survive as a standing structure at a launch site or break apart in the ocean. It was never built with a bridle point in mind. So why not just lift it out with a crane or slide a semi-submersible vessel underneath it and float it out? Both of those are legitimate salvage methods, and both of them get ruled out here for basically the same reason. Crane lifts and semi-submersible loadings are precision operations. They are done in protected anchorages, in still water, where the object being lifted and the vessel doing the lifting are not independently pitching and rolling against each other. When you load something onto a heavy lift ship, You're talking about tolerances measured in inches, sometimes less. You build custom blocks on the deck, almost like a dry dock, specifically shaped to that hull. That's how the US Navy has handled damaged destroyers in the past, ships like the Cole, the McCain, and the Fitzgerald. All three of those were heavy lifted home after collision or attack damage, and all three of those lifts happened in calm, controlled conditions, not in the middle of an ocean with swell running underneath everything. You cannot build a custom cradle for a rocket floating loose in the Indian Ocean. You cannot get a crane vessel into position and hold both the crane and the target object still relative to each other in open swell. Some cranes do have dynamic positioning systems that keep the vessel itself stationary over the water. That technology exists and it works, but it does nothing to stop the object you're trying to lift from rising and falling with the waves underneath it. You'd be trying to thread a lift point on a moving target with a moving tool in open water with no do-over if something goes wrong. So the crane option and the semi-submersible option are both effectively off the table here, at least for the open ocean phase of this recovery. A crane lift back on land, once this thing is safely at port, is a completely different and far more reasonable proposition. That leaves towing. And towing, on paper, sounds like the easy fallback. In practice, it comes with its own long list of failure points, and this is where the maritime side of this story actually gets interesting. Let's talk about the vessels that are actually involved here, because tracking them tells you almost everything about how seriously this operation is being taken. The Go Australis, the vessel that was already on site to watch the splashdown, is an offshore supply vessel. Its job is normally to ferry equipment and personnel out to offshore platforms. It is not rigged for towing. It was never meant to be the tow vessel. It was there to observe and recover floating debris. And floating debris is a very different cargo than an intact multi-story vehicle. The vessel actually built for this kind of work is called the Norman Ranger, operated by Solstad Offshore, a Norwegian company. This is an anchor handling and tug supply vessel, which is exactly the category of ship you want for open ocean towing. Anchor handlers are built specifically to manage massive tension loads, deploy and recover heavy anchor chains for offshore oil platforms, and tow large structures across open water. The Norman Ranger's bollard pull, which is the standard measurement of a tug's towing power, tested by tying the vessel to a fixed point on shore and running the engines up to see how much force it generates, comes in at 280 metric tons. That's a strong number. That vessel has more than enough raw pulling power to move something the size of Starship. Power was never going to be the problem here. Rigging was always going to be the problem. Behind the Norman Ranger is a third vessel, the Skimmer Tide, a multi-purpose platform support vessel from Tidewater. Its exact role hasn't been confirmed, but the most likely explanation is that it's bringing out additional crew and equipment to help physically prepare Starship for the tow, meaning rigging up whatever attachment points end up being used. And that's the actual bottleneck in this whole operation. Not horsepower, attachment. Understand this thing is stainless steel, which means, technically, you could weld something onto it. Welding new hard points onto a hull that wasn't built with them is possible in a controlled shipyard environment. Doing that same weld out in open ocean swell, on a structure that's drifting and pitching independently of whatever vessel you're standing on, is a completely different level of difficulty. You are asking a crew to perform precision fabrication work on a moving, unstable platform, likely from small boats alongside a much larger hull, with no calm anchorage to steady anything. Then there's the fins. Starship has large fins, both upper and lower, the same surfaces used to guide it through re-entry and control its descent. Some people online pointed to those fins as an obvious attachment point, the logic being, just loop a line around one of them and start pulling. That's not how this works. First, those fins would need to be permanently reinforced before you could trust them under sustained towing load, not just wrapped with a rope. Second, and this is the detail almost nobody online was talking about, once you start dragging this object forward through the water, those fins are going to behave completely differently than they do right now, while it's just drifting with the current. Right now, there's no directional force running the length of the hull. It's sitting still, relatively speaking, moving only with the current and the wind. The moment you put a tow line on it and start pulling it forward at any real speed, water starts moving past those fins, and they could start acting almost like diving planes on a submarine, generating lift or downforce in directions nobody has modeled for this specific towing scenario. That's an unknown, not a solved problem. And unknowns in a 2-week open ocean tow are exactly the kind of thing that turns a routine recovery into a disaster. Let's talk about the tow line itself, because this is where a lot of the public confusion comes from. People assume a tow is just a rope and pulling power. It's not. In any long ocean tow, most of that tow cable actually sits down in the water, forming a long curve called a catenary between the vessel doing the pulling and the object being towed. That catenary exists on purpose. It absorbs shock. If you ran a short, tight tow line instead, every time the two objects pitch and roll independently in the swell, you generate sudden snapping loads on that line, and eventually it breaks. So the tow line has to run down into the water and curve, which means it's exerting a downward pull on whatever it's attached to, not just a forward one. That downward force needs a structural point strong enough to take it, and right now, nobody outside SpaceX knows for certain whether this hull has anything built to withstand that kind of load in that direction for that long. We've seen a comparable situation before, and it's worth putting side by side. Years ago, a tugboat named the Vinnick 5 conducted the tow of the SS United States, a dead ocean liner from Philadelphia down to Mobile, Alabama. That tow required a proper bridle rigged onto the ship, attached at points designed to distribute the load so the vessel being towed wouldn't yaw and pitch uncontrollably behind the tug. Even with that careful rigging, when the SS United States hit weather and high winds off the Delaware Capes, the ship actually went sideways to the tow for a period of time. That's a vessel with enormous mass and a huge amount of hull sitting below the waterline, which normally helps stability in a tow. Starship, based on what's visible in the photos so far, is riding very high in the water, meaning there's a lot of structure above the surface and comparatively little below it. That's an unfavorable ratio for towing stability. More surface area above water means more wind resistance, pushing the object around unpredictably, exactly the kind of thing that made the SS United States swing sideways, even with proper rigging in place. There's another useful comparison, and it actually cuts the other direction, showing what a properly planned recovery looks like. The solid rocket boosters from the Space Shuttle program were also recovered from the ocean, and that program worked because it was built around recovery from day one. Those boosters were engineered with flotation in mind and attachment provisions specifically designed for the recovery ships and crews that would retrieve them. Teams trained for that exact operation for years. Nothing about this Starship situation resembles that. This is an improvised recovery of a vehicle that was never meant to be recovered, being handled after the fact by whatever vessels happen to be in reasonable range. Now for the part that matters most, and that almost nobody outside the maritime industry is thinking about. Nobody has clear visibility into whether this hull is even taking on water right now. It's been riding high since the splashdown, but there haven't been many updates on its condition since the last photos came out. Does this vehicle have the watertight integrity to handle sustained ocean exposure, including saltwater intrusion around the engine bells at the base of the hull? Positive water pressure against surfaces that were engineered for the vacuum of space and the heat of re-entry, not for floating for 2 straight weeks. Nobody outside the company knows for certain. And if it's slowly flooding, that changes everything about how this tow gets attempted, because a tow vessel does not want to be attached by a rigid line to something that could suddenly go from floating to sinking mid-tow. Distance is the other factor working against this operation. Based on current tracking, the recovery site sits roughly 812 nautical miles from Dampier in northwest Australia, the nearest reasonable port. At a conservative towing speed of around 3 knots, that puts the estimated arrival sometime around August 11th into the 12th. Maybe they manage a faster pace, maybe 5 knots if conditions cooperate, but that's still the better part of 2 weeks at sea once the tow actually begins. And that's before accounting for however many days it takes just to get a vessel on site, get crews onto small boats alongside the hull, and physically rig whatever attachment system they end up using. Realistically, we are still roughly 2 weeks away from any confirmed arrival back at port, if this succeeds at all. And once it does reach Dampier, assuming it gets there in one piece, that's not even the end of the logistics chain. Getting it out of Dampier and back to Starbase in Texas for inspection likely means another heavy lift, loading it onto or into a transport vessel, this time in the calm, controlled port conditions where a heavy lift actually works the way it's supposed to. So here's where I land on this, and this is my honest read as someone who has spent time around exactly this kind of operation. I don't think this is impossible. Norwegian anchor handling crews are some of the best in the world at exactly this kind of high load, open water rigging work, and if there's a nationality of crew you'd want handling a problem like this, it's them. The Norman Ranger has more than enough raw power, but power was never the question. The question was always whether this specific hull has anything on it strong enough, positioned correctly enough, and reinforced enough to survive 800 plus nautical miles of catenary load, wind resistance, and unpredictable fin behavior, all while nobody can confirm whether it's slowly taking on water the entire time. In my opinion, the honest answer right now is that this is a real coin flip, not a guaranteed win, and the confidence in that original announcement was running well ahead of what the physics of an unplanned open ocean tow actually allow for. So here's the question I want you to answer honestly in the comments. Do you think this recovery actually makes it back to port in one piece? Or does this end with a line snapping, a hull taking on water, and this thing going to the bottom of the Indian Ocean before it ever sees Dampier? Tell me which side of that you're on, and tell me why. Salvage work in any form, on any vessel, in any ocean, is dangerous and unforgiving. People get hurt doing this kind of work, and equipment gets damaged even when everything goes right. So regardless of how this ends, credit is due to the crews actually out there attempting it. Until the next episode, keep watching the water, because this is exactly the kind of story that tells you more about the state of the world's oceans than any headline ever will. If you enjoyed this breakdown, subscribe to the channel, hit the bell, drop a comment with your take, and share it with anyone who thinks towing a rocket is as simple as tying a rope to it. If you want to support the channel directly, there's a super thanks button below, or you can find us on Patreon.